We've been talking about random variables and their distributions. And the main topic for today is averages. That is, how do you compute the average? First of all, what does an average mean, and how do you compute the average of a random variable? And, okay. But before we do that, I want to say a little bit more about CDFs. So because CDF, I think it seems a little mysterious the first time you see it. You know, you have this random variable, and then you assign it a function. It has a function associated with it. What does the CDF really mean? Okay, so first a little bit more about CDFs. I drew a picture last time of what a CDF might look like. I'll just draw a quick picture again. Mainly we're talking about discrete random variables so far, but a CDF makes sense for any random variable. It doesn't have to be discrete. That is, we have a random variable capital X, and we let f of x equal the probability x less than or equal to little x as a function of little x, which is real. Even if x only takes integer values, this is a function that's well defined for all real numbers x. Okay, so that's the function. That's called the CDF. But I want to talk more about, you know, what are the properties and how do you use this thing. So picture a discrete example. By the way, make sure you spell discrete D-I-S-C-R-E-T-E. It's a different word from R-E-E-T. Don't confuse the two senses of discrete, otherwise it could be a little embarrassing. So this is a discrete random variable. I'm going to draw a CDF. It's going to look like a step function. So it's going to jump. So let's draw one whose possible values are 0, 1, 2, or 3. We could have a discrete random variable where it could take on any non-negative integer value, so it could go off to infinity. But right now I'm just looking at one that's 0, 1, 2, or 3. So it has 4 possible values. So on the negative side, it's just 0 because it can't be negative. Then so that the horizontal axis is x and the vertical axis is f of x. And as soon as you hit 0, it jumps. So let's say it jumps to there. Then it stays flat. Now it's also allowed to equal 1 in this example, so it's going to jump again at 1. And I'm putting a closed circle here, an open circle there, and a closed circle here to say that at the jump, it takes the upper value, not the lower value. So it's assuming this value, not this value. And then at 2, it jumps again. And then at 3, it jumps one more time. And that jump is going to take it all the way to 1. So here's 1. And then once it reaches 1, obviously it can't go any higher up. It stays at 1 forever. So this will be, this is one example. Of course, you could also have, if you have one that is not bounded, so it's allowed to go off to infinity, then what you would have would be the jump. It would still keep jumping, but the jumps would get smaller and smaller and smaller. So it would approach 1, but it would never hit 1. It would just get, keep jumping, but smaller and smaller jumps, so it doesn't actually reach 1. This one actually reaches 1. Once it reaches 1, it stays there forever. Okay, and one thing we can notice about this is we're talking about CDFs now, and we talked about PMFs before, just to help connect those two concepts. If we wanted the PMF, geometrically, it's just the jump sizes, because here, this is saying this is the probability that x can't be negative, right? But with some probability, x equals 0, so that's the size of this jump. So this jump is the vertical height of that jump is the probability that x equals 0. This jump is the probability that x equals 1. And this jump is the probability that x equals 2. And this jump is the probability that x equals 3. So the jump sizes are the PMF in this picture. What did we say about PMFs? We said they have to be non-negative and they add up to 1, right? And if you add up all these jumps, that's just saying we're going from 0 up to 1. Okay, so from the CDF, we could recover the PMF. From the PMF, we could recover the CDF just by summing things up. I'll talk a little bit more about that. But just for an example, if we wanted to know, for example, if we took the probability that x is, suppose we want to know what's the probability that x is between 1 and 3. I just made up numbers just for example, but you can make this any a and b. Okay? Well, one way to think about that would be to say that, so suppose we want to find this in terms of the CDF. I'm just doing this as an example to show that if you know the CDF is giving you the entire distribution. So that means from the CDF you can compute any probability you want for x. So then I would say, well, if we take the probability that x is less than or equal to 3, and if we add to that the probability that x is between 1 and 3, let me do this the other way. Suppose we want the probability that x is less than or equal to 3. That there's basically two cases. Either x is less than or equal to 1, so let me put a 1 there, or x is between 1 and 3. All right, so I'm breaking it up into two cases. So that's a 1 there. So this is true just by the axioms of probability, right? I broke it into two disjoint cases to say it's less than or equal to 3. Either it's between 1 and 3, or it's smaller than 1. So I broke it into two disjoint cases, and that's the thing that I was looking for. So that immediately tells us that this probability would be f of b minus f of 3 minus f of 1. I could have called A and B instead. I just did that for concreteness. But that would say, so this gives us the probability of any interval from A to B. Now, if it's a discrete random variable, we have to be very careful about whether these are strict inequality or less than or equal, then it will matter. If it's a continuous random variable, which we'll get to next week, then it doesn't matter if you put less than or equal here or less than. But here, this calculation is completely general. It could be discrete, continuous, or anything. And now I'm trying to be careful about the strict inequality. Okay, so from here, I mean, I'll just write that more generally. A less than x less than or equal b. So if we want an interval like this, well, then it's just f of b minus f of a. So that's just an example showing that from the CDF, then we can compute the probability of an interval like that. Okay, now, so in general, CDFs have three important properties. And we can see all three from the picture, basically. Of a CDF. First of all, it's increasing. And I don't mean strictly increasing, so it's allowed to be flat like that, okay? But it can only go up, not down. And that's, you know, to prove that that's true, all you have to do is look at the definition. If you increase x, you're just making it more and more likely that happens. So it has to be true. Secondly, it's right continuous. I'm not sure if everyone has heard that term before, but I'll just briefly say what that means. Right continuous means, well, first of all, it could be continuous. I'm assuming you know what a continuous function is. This function is not continuous, but it's right continuous, which means that if you take any point and approach from the right, so let's say we took this point here and we look at the limit as you approach from the right, then the value of the function converges to the value at that point. It's not continuous from the left, because if you come from the left and you reach 2 and it jumps, but coming from the right, it's continuous. So all this says is that the jumps look like this, with closed here, open here, or if there are no jumps, that's even better, then it's just continuous. And then the last property is that what happens as x goes to infinity or minus infinity. So as x goes to minus infinity, a CDF has to go to 0. This one actually hits 0, but it's also possible that it would kind of approach 0 and never reach 0, but get closer and closer to 0. And if you go the other way, this one, it hits 1, but in general, it could be approaching 1, but it has to get closer and closer to 1 as you go the other way. Okay, so those are the three properties of a CDF. They're all pretty intuitive, like if you keep a picture like this in mind. And this turns out to be This is if and only if, in the sense that we'll talk about why later, but just so that you know now, if you have any function f that satisfies these three things, then that is a valid CDF. That is, we can find some random variable that has that CDF. Right now we're talking about the other direction, that we started with a random variable, and we said, what does the CDF looks like? Well, in the discrete case, it could look something like that, and in a continuous case, it would, be a continuous curve. But in any case, it's going to satisfy these three things. Okay. So, all right, those are properties of CDFs. One more definition is independence. So we already know what independence of events means, and we've been talking a little bit about independence of random variables kind of intuitively, but I want to say what's the precise definition of independence of random variables. So we say x and y are independent. This is just a definition. X and y, which are both random variables, are independent if, and then the idea is simply to relate random variables back to events. So we would say the probability that x is less than or equal to little x, probability y less than or equal to little y, factors. Remember the slogan, independence means multiply? So if you have this thing here is called the joint CDF. And we'll be considering those much later in the course, but what that's saying is look at the probabilities simultaneously for the x and the y. But it's saying independence means you can just multiply those two things. X less than or equal to x, y less than or equal to y. Then this has to be true for all little x, little y. So that's saying that the events, remember this thing, x less than or equal to little x? That's an event. It's saying that that event is independent of that event. Okay, so we reduced it back to independence of events. Now, this looks a little bit unwieldy. So usually in the discrete case, it's easier to work with the PMF. Like that jump function I drew, I'm glad it's kind of covered up now, because it's hard to think about these jumpy functions, right? I don't really want to deal with all the jumpy functions. It's much easier to use the PMF. So in the discrete case, this equation is equivalent to just saying that the joint PMF, which is the probability that x equals x and y equals y, is the product of the individual PMFs. So I hope this definition is pretty intuitive. You can show that this is equivalent to this. It's kind of tedious, but there's nothing really difficult about it. But I hope that this equation is intuitively makes sense as far as what independence means, because this says that intuitively knowing the value of x tells us nothing about the value of y. So that means that the event x equals x should be independent of the event y equals y. That's what that says. This definition won't work in the continuous case that we'll get to later, because in that case, this is just going to say 0 equals 0. But in the discrete case, this is a lot easier to work with. It just says we can factor this into the individual PMFs. Okay? So that's what it means for random variables to be independent. And in general, as I said, in the discrete case, it's easier usually to work with the PMF than the CDF. For example, in the discrete case, if you want to know the probability of anything, any event, just sum up the PMF over the relevant values, and that's it. So okay, so that's independence. All right. So now we're ready for averages. I'll just start with something very, very simple and familiar, and then we'll just generalize and extend it and see how do we really work with averages of random variables. So averages. Averages, well, you know that there's more than one way to average a bunch of numbers, right? But if we just say, there's like mean, median, and mode, and different weighted averages and all these things. But if you just say the word average without any kind of clarification or anything, usually what you mean is the mean, right? So that means So if we just say average without any further clarification, you can assume that that's the mean. That is just the ordinary average that you add up the numbers and divide by the number of numbers. And it's also called expected values. All of these are the same thing. So we use those interchangeably. Okay? So we want to know, how do we take the average of a random variable? And that's a very, very important concept because, first of all, remember, this random variable is this thing that we don't know what value it'll be before we do the experiment. Then we do the experiment, and we actually may get to observe the value. But beforehand, we may want to make some predictions, right? We may want to say, on average, what's going to happen. Okay, so that's one reason. Average is a very, very familiar concept. But actually, the importance goes beyond that, too, because you could just say, well, the average is only just telling you like a one-number summary of the center of the distribution in some sense. And that's important, but still, that's just a one-number summary. You might have a very complicated distribution, and one number is not going to be enough. So later, we're going to talk about variance and standard deviation and measures of variability. Well, it turns out that if you want to measure how spread out the distribution is, you still need to use this concept anyway. So we're going to keep using this over and over again, not just for finding the simple average, but we're going to find averages of various functions of random variables. Okay, so to start with something very simple, if we just had the numbers 1, 2, 3, 4, 5, 6, then if we want to average them, then we're just going to add them up. 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6 equals 3.5. Okay? Well, that's the starting point of averages. Very, very simple. And by the way, does everyone know that you can, if you want to do this, you don't actually have to add up all the numbers. You can just add the first one and the last one and average those. That is, the average of 1 and 6 is 3.5. That's true for any arithmetic sequence. That's something I should have put on the math review. I'm just going to mention briefly. How many of you know the story of like Gauss at age 10 and the numbers from 1 to 100? Okay. Well, let me quickly, a lot of you have seen that story. I'll tell it to you very, very quickly for those who haven't seen it. Gauss was one of the greatest mathematicians of all time, and when he was a little kid, his teacher was annoyed with the class and asked them all to add up the numbers from 1 to 100 just to kind of keep them busy so he could do something else. And so thinking that would keep, these were like little kids, and he was thinking that's going to keep them busy the whole day so he doesn't have to deal with these kids. And then so Gauss saw these numbers and he said, you compare, Gauss immediately saw, you compare the 1 and the 100 and the 2 and the 99. 1 and 100 is 101, 2 and 99 is 101, 3 and 98 is 101. So all the pairs add up to 101, so he just immediately wrote down, 101, and there's 50 pairs, equals 50, 50, and just immediately, wrote down the answer. So that's just an example of what I was just saying about an arithmetic series. So it's useful for, in this class, but it's just useful in general. Everyone should know that if you want to add up the numbers from 1 to n, if I want to average the numbers from 1 to n, that's n plus 1 over 2, which is what I just said. It's the same thing as averaging the first number and the last number. And to prove that, you could do just something similar to what Gauss did. Of course, you could put the n on that side, but I put it here just because this is saying if we average the numbers from 1 to n. So that's called an arithmetic series, as opposed to, we've seen geometric series. Geometric series, you multiply by a constant every time. Arithmetic series means each term you add a constant. So for this one, we're adding 1 each time from one term to the next. But as long as you're adding a constant each time, what I said will be true, that you just average the first and the last. Okay, so that's really, really easy. Now let's do, not really a harder problem, but something that's a little bit different, in the sense that I wrote down 6 distinct numbers here. Let's think what would happen if we had some repetition. So suppose we have, I'll sort the numbers, but the average is not going to depend on what order I write them in. Suppose we had 5 1s and 2 3s and 1 5, and we want to average these numbers. Okay, so I have 8 numbers here. Notice that there are 2 ways to do it. This is like really, really simple arithmetic, but it's also a really key concept that's going to help us when we get to random variables, to keep in mind the fact that there's 2 ways to do this. One way to do it is just the same thing I did, just add up these 8 numbers and divide by 8, right? So add and divide by 8. Okay? But notice we could also do it a different way, which would be to group the 1s together, group the 3s together, and then the 5 is its own group, right? And then I could average these, but when I average these, obviously I'm not going to give them equal weights. I'm going to give this higher weight because I have 5 times as many 1s as 5s. So I would do a weighted average, which would be, I'm giving this term weight 5/8 because there's 5 1s. And I'm giving the 3s weight 2/8. And I'm giving the 5 weight 1/8. And that would be the same, right? Just simple arithmetic. But the key point is that I can take the ungrouped average, or I can group them according to common values and then average those. As long as I put the correct weights here, it has to be the same thing, right? I don't actually have to do the arithmetic. I don't actually want to compute this number. Does anyone doubt that those would be the same? All right. So that's a pretty simple idea, but very, very crucial for understanding what's going on. So that's a weighted average, right? Where these terms are the weights. And notice the weights are non-negative and add up to 1, right? 5/8 plus 2/8 plus 1/8 is 1. Okay? So we have some weights. That's a weighted average. Okay? So if we just do something like this, this is an unweighted average, right? Because we're giving each of these has weight 1 over n. So we'd call it unweighted if they all have the same weight. And this one is weighted because we have different weights. Okay? All right, now let's extend this to random variables. So we want the average, and we're talking about the discrete case now. Everything will be analogous for the continuous case, which we'll get to later, but right now we're doing discrete. So average of a discrete random variable x. And the notation, standard notation in statistics is to write E of x. E means expected value. E of x equals, and now I'm just gonna use this same idea that we're summing up values times weights, and the obvious weight to use would be the probabilities, right? So if I want to know the average of x, and x has different possible values, I'm going to give higher weight to the values that are more likely, and I'm going to give low weight to values that are unlikely. That's all we're doing. So therefore, we just write the sum over all x of x times the probability that x equals x. That's the PMF, and that's a value. This is the easiest way to write it, but we could also write this as, we could call this thing like, index it by, here I'm assuming that we're not summing over all real x, right? We're summing over all x, well, let me write that out, summed over x with probability x equals x positive. So we're only going to need to sum over a finite list or an infinite list, but not an uncountable list, for those of you who know what uncountable is. So for example, if x takes on positive integer values, are its possible values, then we would just sum over all positive integers of, a positive integer times the probability of that, okay? So that's completely analogous. All right, so let's do a couple examples. Simple examples to start with, and then we'll do some harder examples. The simplest thing we could start with is a Bernoulli. Sorry. Bernoulli P. Let x be Bernoulli P. And let's save some room. Bernoulli P means can only equal 0 or 1. So that's very, very easy to deal with. So we can do this one very quickly. Let's just write it down. Expected value of x equals 1 times the probability that x equals 1 plus 0 times the probability that x equals 0, but that term is 0 anyway. And that's just equal to p by definition. So a Bernoulli p has expected value p. Very, very easy calculation. But even though this is so simple, there's actually something deeper going on. Let's suppose that x equals, let me give you a specific example of a Bernoulli random variable. Suppose we have some event A that we're interested in, and we let x equal 1 if A occurs, 0 otherwise. Okay? That's called an indicator random variable, and we'll be using those a lot. So an indicator random variable is just saying 1 if the event occurs, 0 otherwise. By definition, that's Bernoulli, right? Because it's either 1 or 0. So what we've just shown is that, well, the probability that it is 1 is the same as saying the probability that A occurs. So therefore, E of x equals P of A. Very simple looking equation. Okay. Well, and that's just the same thing. The expected value is p, and p is the probability of A. So very, very simple. But I actually think this equation is pretty fundamental. I call this thing the fundamental bridge, which is kind of an overly grandiose name for such a simple little equation. But the reason I think this equation is really fundamental is that this bridges between expected values and probabilities. This says that any problem you want in probability, that is, if you have any event A, you want P of A. If you want, you can always reinterpret that as the expected value of an indicator. So this bridges between E and P. So in a sense, we could have started with expected value on the very first day of this class and derived probabilities from expected values. We could have gone the other way. So you can go between P and E that way. So that's very useful. All right, let's do a harder example than the Bernoulli. The obvious next one to try would be the binomial. So first I'll write down the definition and we'll work it out. But then I'll show you that actually there's a much better way to do this problem. But it's good to see more than one way to do it. So we want the expected value of a binomial. Again, I'm just going to write down the definition. I'm going to sum up value times the probability of value, right? So binomial takes values k equals 0 to n. The value is k, and then we multiply by the PMF, which by now you know is n choose k, p to the k, q to the n minus k. Okay, so we have to do this sum somehow. Well, without the k, that's just the binomial theorem, and we know it equals 1, and that's the PMF sums to 1. With the k, though, and it sounds like, you know, that k is kind of in the way, and we have to deal with it somehow. Luckily, this thing, k and choose k, is one of our stories that we talked about when we were doing stories for counting. Of course, you can just do some algebra with this, but we talked about the fact that k n choose k is the same as n minus 1, k minus 1. Because that was the story where we have n people and we choose a committee of size k with one person as president. So you can either first choose the president, then choose the rest of the committee, or choose the committee, then choose the president from someone on the committee. So that's the same thing. The reason I wanted to rewrite it this way is k depends on k, and that's annoying there. N does not depend on k. That's just a constant that comes out. So we can take out the n, and let's also take out one of these p's so that I can make k minus 1 and k minus 1 match up. So we're going to take out np times the sum, k equals, let me actually start this sum at 1 rather than 0. It doesn't change anything because if k is 0, it's 0, so that term doesn't do anything. So I'll start it at 1. And then just whatever's left over. N minus 1, choose k minus 1, p to the k minus 1, q to the n minus k. Now it looks a lot more like the binomial theorem again. In fact, this is exactly the binomial theorem. If let's say we let j equal k minus 1. So j goes from 0 to n minus, I'm just making a change of variables. I'm letting j equal k minus 1. So now it's going up to n minus 1. K minus 1 is j, so that's n minus 1. Choose j, p to the j, q to the, and then the total has to be, so it's n minus j. The total has to be, the total of these exponents has to be n minus 1. So I'm just letting k equal j, k equals j minus 1. Let's see, so that becomes a plus? I guess that's a plus. Well, that doesn't look right. Pull out a q? I don't want to pull out a q. K equals j. All right. The way this goes is that, so we're letting j equal k minus 1. It should be a what? N minus 1 minus j. N minus 1 minus j. Like that? So j is k minus 1, so k is j plus 1, right? So I let k be j plus 1, so they're both minuses, okay? Is that okay now? All right, so now this looks better because now if we add up j and n minus 1 minus j, we get n minus 1. Now it looks exactly like the binomial theorem. So this whole thing is just 1. So this whole this part equals 1, so the whole thing is just NP. That's why I didn't want to pull out a q, because I knew it's going to work out to NP. So we took out NP. Whatever's left is 1 by the binomial theorem. Okay? So that's kind of an annoying calculation. Here's a better way to do this. The key idea, actually not just probably, definitely the single most important property of expectation is what's called linearity. So we're going to use linearity over and over and over again. The single most useful thing about expectation. Linearity says that the expected value of x plus y, you can just add them up. And this is always true, even if x and y are dependent. I think this is kind of intuitively seems fairly obvious if x and y are independent, but it seems surprising, at least to me, the first time I saw this, that even if x and y are dependent, that's still true. So we'll prove that this is true next time, but for now, we can feel free to start using it, and then I'll fill in the proof next time. But I wanted to show you how this is useful, and then we'll come back to the proof. One other thing about linearity. Linearity is normally stated as two things. One is this, and the other one is that we can take out constants. And this one is kind of more obvious, but also useful. So if c is a constant, we can just take it out. Okay? But this is the most interesting one. Expected value of the sum is the sum of the expected values. All right, so now let's redo this binomial thing. Because this was pretty annoying to go through this whole thing, and I even had a head start because I knew that this particular identity would be useful. But if you didn't remember this, then you start expanding out some factorials and messing around with it, and hopefully you can eventually get to this point. But it'll be a lot of work. Let's redo that a better way. Redo the binomial. Well, I kind of didn't leave much space here, but we don't actually need much space because all we have to do is think about linearity. Remember the binomial, NP, we can think of it as the sum of n IID Bernoulli P's. Each of those Bernoulli P's has expected value P, and there's n of them, so it's n times P by linearity. So I don't know about you, but I prefer this method to this method. So that's a calculation you can all do in your head. Just each one is P, each Bernoulli has expected value P, and there's n of them, so it's NP. Since, I'll write that out as well. X equals x1 plus blah, 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 plus xn, where xj's are Bernoulli P. Now, actually, for the binomial, we can actually think of these as independent Bernoullis, but this says even if these Bernoullis were dependent, it's still true. It's still going to be NP. So this is just then extremely easy, but by linearity. Okay, let's do another example. Another distribution we talked about last time was the hypergeometric. And just to take a concrete example again, let's say we have 5 cards, 5-card hand, an example I talked about last time, and x equals, from a deck of cards, and x equals the number of aces, so just coming back to that example. I can phrase it this way, or I can phrase it in terms of the elk, or I can phrase it in terms of marbles, or how, many different ways. It's the hypergeometric problem. And we want the expected value of x. Well, the hypergeometric looked, you remember it had that PMF involving these binomial coefficients and this complicated looking thing. It would be kind of a pain to try to do that. The hypergeometric looks pretty complicated. But instead, let's just think in terms of indicator random variables. So let's let xj be indicator of jth card being an ace. Now, I didn't say that the cards are in any particular order, but we can assume that there's some order, like the cards get dealt to us one at a time, or there's implicitly there's an order in that you're holding these 5 cards and there's one on the leftmost. You have them in some order. It doesn't matter what order they're in, but it helps to think that they are in some particular order. So it makes sense to say, okay, first card, second card, and so on, just so that I can concretely say I have indicators for each of the 5 cards. So I have 5, j goes from 1 to 5. I have 5 of these indicator random variables, okay? So therefore, we can think of x as just being the sum of these indicators, right? That's just how we count, right? If we want to count to 3, you go 1, 1, 2, 3. You just add 1 each time you want to increment. By linearity, that's just the sum of these. That's linearity. By symmetry, so this is linearity. This step is indicator random variables. And then by symmetry, that's really just the same thing 5 times. Symmetry. There's no reason to think that the second card has a different distribution from the 5th card, right? It's completely symmetrical. So therefore, we can just write down the E of x1. Actually, let's write one more step. E of x1 equals the same as the probability that card is an ace. So this is equal to 5 times the probability that the first card is an ace. That's the fundamental bridge. Probability that the first card is an ace, well, 4 over 52, or 1/13. So this is just 5/13. Okay? So I wrote this out in a lot of detail just so you could see exactly what steps were being used. But this is also one that you could do in your head, right? It's just saying I have 5 indicator random variables. Each one is 1/13, so it's 5/13. So it's actually completely analogous to this, where it's just something you can immediately do in your head. That the difference is just that in this case, the xj's are dependent, right? Because, for example, if the first 4 cards are aces, the 5th one couldn't be. But linearity still says that it's still true. So using these tools together is often a very, very powerful strategy. Indicators, linearity, symmetry, fundamental bridge, and you can solve a lot of problems. So I just did this as a concrete example, but in general, that this gives you the expected value of a hypergeometric. Any hypergeometric that you want, remember hypergeometric from last time, the marbles or the elk, it's going to be the same thing, right? Same calculation. And even though in the hypergeometric the trials are dependent, what this says is that for the expected value, it still looks as if it were binomial, even though it's not, for the expected value. For other things we'll do later, we'll see differences with the hypergeometric. But just for the expected value, it's just n times the probability that an individual one has whatever property. Okay, so we'll do more examples with indicators and stuff next time. But the last thing for today is we need one more famous distribution. And that's called the geometric. Not to be confused with the hypergeometric. There's very little in common between the geometric and the hypergeometric. Okay, so this is our next famous distribution, the geometric distribution with parameter p. As with the binomial, we're assuming that we have Bernoulli trials, independent Bernoulli trials, for example, flipping a coin, but just anything where you're repeating the same experiment over and over again with independent Bernoulli trials. Each trial has the same probability p of success. And the story of the geometric is that it's the first, it's how many failures before the first success. So this is the number of failures before the first success. And you have to be a little bit careful with this because some books count the success as part of it and some exclude the success. And I slightly prefer the convention to just count failures before the success and don't include that success. But you just have to be consistent and careful because depending on where you look, you'll see different conventions. Number of failures before the first success. Okay, so let's write down the PMF. And then let's find the expected value. So here's the PMF. The possible values are 0, 1, 2, 3, and so on. And let's let Q, so let's let X be geometric P. So the interpretation is we're just repeat, unlike the binomial, in the binomial there's a fixed number of trials, n, right? And in the geometric, you just keep, if at first you don't succeed, you try, and try again until eventually you succeed, and then you count how many failures you had up until that point, okay? So, and as usual, we'll let Q equal 1 minus P. And just to draw a little illustrative picture, here's how it goes. It could be that well, suppose let's write F for failure and S for success. So maybe we got 5 failures and then a success, okay? The probability of that happening, so in this case we would say X equals 5, right? Because I'm counting the number of failures until the first success. That's the only, this sequence is the only way that could happen, right? 5 failures and then a success. So X equals 5 corresponds exactly to this sequence, and the probability of this sequence is Q to the 5th times P, right? Because we had 5 failures and then a success. That's just the probability of that sequence. So in general, this is going to be Q to the K times P, where K goes from 0, 1, 2, 3, and so on. Okay? So that's the PMF. Let's check that this is a valid PMF. Why is this valid? Well, to check that these are non-negative, so to check this is valid, we have to add these up and see if we get 1. So if we add up PQ to the K equals 0 to infinity, we can take out the P because that's just a constant. That's just P. Now the sum of q to the k, that's just a geometric series, right? The sum of this geometric series is 1 over 1 minus q. 1 minus q is p, so that's just 1. And that's what we wanted. So that's why this is called the geometric distribution. It's because this thing is a geometric series. Just like for the binomial distribution, you get the binomial theorem. That shows that the PMF is valid. All right, so now let's do the expected value. So again, there's more than one way to do this. Let's take, so we're letting x be geometric p, and we're going to try to compute the expected value of x, first of all, by the definition. Definition says we just write down the sum of values times probabilities. So we go k equals 0 to infinity of k, p, q to the k. I just wrote down that PMF times the value. So that's the definition. And, you know, p is a constant, so we can take out the p. And we can start the sum at 1 because it's 0 at 0. K q to the k. So without this k in front, that would just be a geometric series, very easy. With the k in front, that's kind of annoying, okay? And we need to actually, so as far as a strategy, here's our scratch paper. We see that k in front and we don't know what to do with it. The strategy is start with things that we know and then try to reduce it back to what we're looking for. So the only thing, you know, I know that's related to this is the geometric series. I know how to do this without the k. So without the k, we would say, well, we have a geometric series. That's what I just did. Okay? Now somehow I want a k in front. Somehow I need to get from q to the k and get that back to k in front. Well, one idea would be to take the derivative, right? Because if I take the derivative with respect to q, then I'll get kq to the k minus 1, then I have a k in front. So let's take the derivative of both sides of this equation. So that's going to be kq to the k minus 1. And I'm going to start the sum at 1 because it's 0 at 0. I just took the derivative. I exchanged the derivative and this sum, but it's OK to do that. And then I have to take the derivative on the right-hand side. Well, what's that? It's minus 1 over 1 minus q squared, and there's another minus from the chain rule. So it's just 1 over 1 minus q squared. That now looks very, very similar to this, right? The only thing bad about this is that we are missing, this is q to the k minus 1, that's q to the k, but that's easy to fix. Just multiply both sides by q. So the sum of k q to the k equals, I'm just multiply both sides by q, so that's q, and the denominator, by the way, is just p squared, because 1 minus q is p, so that's q over p squared. Okay, so now this is just pq over p squared equals q over p. So that's a trick for doing a sum like that. That, you know, we start with something we know, then, you know, try like derivatives and things like that. All right. Well, we only have 2 minutes left, but I want to show you. This is still required some calculus and a clever trick. I want to show you. Here's the story proof method. Let's let c equal the expected value of x, and we're trying to solve for c. I just want to give it a more familiar looking notation, c. We're trying to find c, okay? Well, let's just think about it in terms of, you know, flipping a coin with probability p of heads over and over again until the coin lands heads for the first time. Count the number of failures. So we want to solve for c. Well, there's two cases. This is very similar to the first step analysis, like the gambler's ruin. Either the first coin flip is heads. In that case, x is 0 because we had no failures, right? So in that case, it's 0, and that case happens with probability p. That means success the first time. The other case is failure the first time, okay, which happens with probability q. Now, if it's failure the first time, we have that one failure, but then notice it's the same problem again, right? The coin is memoryless. The coin is not out to get you. The coin's not trying to help you. It just just a coin. One failure, then the problem restarted. So it's the same problem again. So it's plus C again. Okay, so what's that? That's just Q plus CQ. Solve for C. 1 minus Q is P. So if we solve that equation, we get Q over P. So this way I like more because we don't need to use any calculus. We just write down, what does it mean to be geometric in the story. This way we use a little bit of calculus, but either way we'll get Q over P. Okay, so that's all for today. Have a good weekend.